Another important point in unstructured grids is how do we calculate the mass flow at the boundaries? This is a very important issue, and it is connected with the fact that we are using co-located variables. If you have pressure, velocities, temperature, turbulence quantities, everything, density, everything is stored in the same point. What happens is that is inherent to the finite volume technique to calculate the mass flow at the boundaries, because at the boundaries there is mass flowing and mass is carrying momentum, is carrying energy, is carrying turbulent kinetic energy. So mass flow, which I'm denoting here by the red arrows, mass flow needs to be calculated at the boundaries, but you don't have velocity there. Your velocity is right here. So you need to calculate the velocity at the boundaries. So this issue is related to the fact that you have a collocated variable. Imagine if you have staggered variables that use pressure here and the velocities stored at the surface, at the boundaries of your control volume. That is the best scheme, because then you don't need to do any average, any calculation of the mass flow at the boundaries, because the velocity is there. It's just to multiply the velocity by density and by the area, and you have the mass flow on that boundary. And see the importance in having the mass flow very well calculated. I just mentioned mass flow carries all other properties. If you don't have a very good calculation of the mass flow, you are, let's say, introducing errors, and also in the other variables, not just on the mass flow, because mass flow carries all the other scalars. It's like momentum in x, y, and zeta direction, energy, and so on. So this topic, I'm just bringing it now, but we will discuss it when we see the element-based finite volume method, because the element-based finite volume method is also collocated. Normally it's collocated. And then the same issue will appear there. And then I'm just now, let's say, trying to light this problem, but we will discuss this problem later. But it is very important. This is really very important. Another topic that I want to talk a little bit, which is general, still general topic, is the equation system that we have and how it is related with the pressure velocity coupling. So this is the system equation that we have to solve. Mass conservation, momentum conservation, the x component of the momentum conservation, y component of the momentum, zeta component of the mass momentum, energy, equation of state if it's a compressible flow. Equation of state pressure relate to density and temperature. And if you have a single phase flow but with many components, single phase flow with many components, you will have the concentration of the components. So it will be mass conservation of the component. This is transport equation for K, turbulent kinetic energy. Transport equation for epsilon, which is the dissipation of kinetic energy. So this is the system you have to solve. You know, every equation, when you integrate it, will give one linear system to be solved. So there are several linear systems to be solved, except the a state equation which is not a partial differential equation, so it does not give us a linear system. It's an algebraic equation. But then all the rest are partial differential equations, and the integration of the equation will give us a linear system to be solved. Now you can play with this linear system. What we are going to do with that? Solve it, put it all together, solve it simultaneously, or segregate it. That's what we are going to see right now. Remembering that Navier-Stokes equation has a very delicate coupling. Why? Because mass conservation, it does not play, let's say, an active role in the solution. Because mass conservation has no pressure. Mass conservation, there is no pressure on mass conservation. So one of our variables we are going to see now in different solvers that lacks the pressure here in order to have, let's say, a better and a strong linear system to be solved. Mass conservation, we could call the mass conservation just a verifier, because thinking in given to the momentum equations a certain pressure gradient that generates velocities which you have to introduce in the mass conservation equation and check if it satisfies. If it doesn't satisfy, what you have to do is to choose another pressure gradient to introduce here to get another velocity, and then you check again in the mass conservation equation. The mass conservation equation, just if the mass conservation equation could talk to us, they say it didn't satisfy. Your velocity didn't satisfy. Try another one. So then you have to go back and say another pressure will give another velocity field which will try to satisfy mass conservation. You have to check that, and you have to find a pressure which drives velocity in the momentum equation which satisfies mass conservation. So there is an algorithm on that, because pressure is not there, especially if you are using in a segregated solver. So this coupling is delicate, is tricky, because a good, let's say a strong system of equation is the system that you have all your variables appearing in all equations. Say, in the mass conservation equation, if you are trying to solve the pressure velocity, should be pressure U, V, and W there. In momentum conservation, you have to have a pressure U, V, and W. So the good system to be solved is when all variables appears in all equations. Then you will have a linear system with no zero coefficients. It's a better system. It's a better conditioned system to be solved. Our system is not like that, because pressure is not in the mass conservation equation. So then there are several ways of solving this coupling. And then we can divide it in two main categories: the pressure-based and a density-based solvers or methods. What are the pressure-based methods? The pressure-based methods are the ones that transform the mass conservation equations in one equation for pressure. There are several algorithms you can do, but what are the algorithms are named? A pressure-based algorithm is the one which they pick up the mass conservation equation and transform the mass conservation equation in an equation for pressure, per equation. And the density-based is the one that uses the natural appearance of the mass conservation equations, uses the mass conservation equation for solving for density. Then you have the mass conservation equation, density is there, you use the mass conservation equation to get the density, and the pressure is obtained through an state equation. Then this is suitable for compressible flows, right? Because if it's incompressible flow, there is no longer equation of state to be used. So pressure based is a method which can solve compressible as well as incompressible. This is also an important thing. Let's not think that the pressure-based methods is suitable only for incompressible flows. No. Pressure-based methods are also applied to compressible flows. The only thing you have to do is to have some kind of pressure density coupling. And who attended the computational one course remembers that the last chapter of our course on that occasion was showing that the same methods that were used to solve the incompressible equation can be extended to solve compressible flows using some kind of coupling between pressure and velocity and density. It's still a pressure based because the continuity or mass conservation equation is transformed in an equation for pressure. So this is really important. I want to keep in mind. Pressure based is not only suitable for incompressible flows, it's also for compressible and incompressible. Density based is the one which recovers the density from the mass conservation equation, and then pressure is solved, is obtained with the state equation. But then if you have a state equation, it's compressible flow then, that's suitable for that. So pressure based and density based. And then how do you handle the linear system? It's more related with the pressure velocity coupling or pressure velocity density coupling. How you handle the linear systems which are, you know, results of your discretization. And then we have two main routes to follow: segregated solution or simultaneous solution. What do you do in what we do in the segregated solutions? All equations is solved, every equation or all equations are solved independently, iterating until convergence. So we will have something like that. I will have a matrix A of u times the u velocity is equal to a b du. I will have a similar equation and but all the equations like that, you know, it's a pressure based. I have matrix for P. This is the transformation of the mass conservation equation and equation for pressure. Pressure. You solve one by one, but they are all coupled, right? Because when you are solving U for the U velocity, where are the V velocities and W velocity which shows up in Navier-Stokes equation? They are in the coefficients. They are the coefficient. You have to change the coefficient. This is a non-linear problem. So when you do this iteration, you are iterating because of two reasons. nonlinearities and coupling. Because you go solving the equations, this matrix changes because of the coupling, and pressure is there, and then you change pressure, so you are solving the pressure velocity coupling and also the nonlinearities. What is almost written here. Since nonlinearities and coupling is involved, this approach is prone to divergence and difficult for the solution. It's clear. You solve one equation and you are using variables from all the other equations that you solved in the previous iteration. So there is a strong influence of the variables which are changing during the iteration, during the iterations. And this is sometimes difficult to converge, you know. Of course, on the other hand, it takes less storage than simultaneous, where we have a large matrix to be solved. But, you know, this is more difficult to solve when it's in the segregated fashion. I put here some observation because these are the software that I know. In Fluent, pressure-based and density-based can be solved in a segregated way. If you go in Fluent software, there is the pressure-based there is the density-based, both can solve in a segregated way. In the simultaneous solution, you put all variables together. You put together all these equation systems. Of course, it's not done yet with all the equations. What is done simultaneously is U, V, W, and P. The pressure and velocity are put together because this is the more difficult coupling that we have. So normally in the segregated approach, you have something which is a matrix where you are solving U, V, W, and P. You have all the entries here, you know. Here too. And then you solve, let's say, temperature. You solve, by the way, turbulence kinetic energy. Okay? And all other scalars. You solve coupled. We call coupled, but this means simultaneously. We solve simultaneously U, V, W, and because when you do that, you get rid of the need of pressure velocity coupling because you are already coupling. You need some kind of coupling here between pressure and velocity because you're solving segregate. When you solve here, pressure and velocity are already coupled in the linear system. And then the other scalars, then you solve the other scalars one by one. You go back and forth, iterating. Here we have still, you need to iterate it because this matrix will depend on the other variables, nonlinearities, and the coupling is taking into account when you solve it simultaneously, U, V, W, and P. But nonlinearities has to be still with iteration on this matrix. And then this is the simultaneous solution. I prefer to call simultaneous and not coupled because when you solve this one, at the end of the simulation, you solve the coupling. Am I right? The coupling is solved when you do all that. So at the end of the problem, you solve the coupled problem. But then it's better to say simultaneously, because here you are not solving U, V, W, there is another, U, V, W, and P, you are not solving all at the same solution is one, then the other one, then the other, and then this is segregated. But then I put all together, it's simultaneously. Segregated is a synonym of, let's say, one after the other one, after the other one, is segregated. So they are not at the same time. Don't confuse it same time here with the transient. The solution is not the same at the same moment in the algorithm. And then one, then the other one, using information of the other one, which is this nonlinearity coupling involved. And when it's simultaneous, the variables are being solved simultaneously, all together. The only thing which remains is the necessity for iterations because of a nonlinearity, but the coupling is considered. You know, then I prefer to say simultaneous than coupled, but it's synonymous in the literature. I have some observation about the commercial softwares. I'm talking about Fluent and CFX and CFX because I don't know the others. To give an example, in Fluent, density-based approach is also possible to solve simultaneously. What are the variables that you solve in a density-based solver and solving simultaneously? If it's density, so it's compressible flow. What are you solving here? Is rho, U, density, and W. This is what you solve simultaneously when the flow is compressible. You take this from the mass conservation, momentum. And then when you solve that, and then of course you are going to solve temperature also. Some way, you're going to solve the temperature. Then with the density and with the temperature, you solve pressure using the state equation, because the problem is compressible flow. So simultaneously solving density-based, which means using the mass conservation equation to solve for density, this is the coupling. If it's incompressible, then you solve for pressure, but not always. I just said that CFX, in CFX, compressible as well as incompressible flows are handled simultaneously with a scheme which relates pressure with density and pressure with the velocity, and the equation, it continues to be pressure here. But then is the scheme that I just talked, which is in the chapter 7 of the book, which is the pressure velocity and pressure density coupling. And then this is important. I know it's not so easy to the mass conservation. You can, I think my next slide will tell that. You can extract density from here, from mass conservation. And then you find pressure as a function of density and temperature. But what we can do here also, from mass conservation, and to use an algorithm with, in the mass conservation, you substitute U as a function of pressure, and density, which appears here, as a function of pressure again, compressible flow. And then you can extract pressure here. And this can be for compressible and incompressible. So it's possible to solve simultaneously U, V, W, and P. It is being solved a compressible flow. You know, you know where that. Yeah, this is the slide, which tells us how pressure-based methods work. I already mentioned that the pressure-based methods works, transforming the mass conservation equation an equation for pressure. So the pressure field should generate velocities which satisfies mass conservation. Then you have a pressure field, you have the energy equation, you solve for temperature, you have the momentum and the state equations. The momentum, you take velocities. From the state equations, you get densities. You get densities. If you have velocities and densities, you can put them here. Velocity, that's what you have in the mass conservation equation, velocity and densities. Then you put velocities and densities in the mass conservation equation, velocities and densities as function of pressure. Velocity as function of pressure. Then comes the very well known simple, simplex, all the algorithms that you know, where velocity is written as a correction equations in terms of pressure. Here. And then the algorithm for pressure density coupling writes density as a function of pressure. Density as a function of pressure means compressible flow. And then you put all this in the mass conservation. There is an error because you don't know if this pressure field is correct. And then you correct the velocities in densities with pressure. So here comes the pressure velocity density methods. All these methods that I'm writing here, you see many others, they were developed for incompressible flows, but they can be adapted for density variable too, so it's compressible. So in the CFX, there is only pressure-based methods. And the equation for pressure comes from the mass conservation equation, considering the variation of density with pressure and considering the variation of velocity with pressure. Is it clear? And then is it just a pressure? Is it just a pressure-based solver? Then you can have a pressure-based solver for compressible as well as incompressible flow. You know, and then some final remarks on that. Keep in mind that we have always a very important coupling in fluid mechanics. It's U, V, W, and P. This is the strong part of the problem. Followed by the solution of other scalars. And then the other scalars, we solve each matrix for each one. But when possible, it's better to put U, V, W, and P together. Of course, if you have a very big computer, you could put everything together, right? Just a big matrix. U, V, W, P, and temperature, and K, and epsilon, and all the variables. A very big matrix to be solved. You solve everything coupled. The only thing you have to do is to change this big matrix, modify this big matrix in terms of nonlinearities. If the coefficients involve the variable, you have to change that. If it would be a linear problem, then you solve altogether, it's done. You have the solution. You need to iterate because, but the important problem, in my opinion, this will be wasting of time. Because it's difficult to, sometimes the equation, one equation that you solve independently is not very well coupled with the rest. So why to put everything together to solve simultaneously if there is no strong coupling? You know that in fluid mechanics sometimes, because you have so many equations to be solved, sometimes you don't need to solve all of them in the same iteration cycle. You can leave some equations dormant, you know, without being solved for several iterations. Then you bring it into the iterations again, because it doesn't change too much. So why to solve equation if the change in that variable is so small that doesn't interfere too much in the solution procedure? So, but you can see that's not an easy matter to look to this system and say this equation can be without solution for a while and so many iterations, then put it back to the iteration cycles and now remove it. It's difficult to do that. And it's difficult to do that even in a general software, you know, because a general software is created, is developed to solve a wide range of physical problems, and they may be different. It would need to have some kind of artificial intelligence which recognizes the problem and says this equation cannot be solved, or the analysis of the user, you know. This is not done, of course. And the U, V, W, and P problem can be solved simultaneously or segregated. Solving in a segregated manner, if you solve one by one, there is the need for some coupling. Simple, simplex, prime, piezo, and many other, the simple-like methods. No? When the equations are solved simultaneously or coupled, it does not require a PV coupling. Of course, if you solve here, U, V, W, and P, there is no need for simplex, for simple, for simpler, for any other method. So the simultaneous solutions appear like that. It's a matrix there. Of course, when you this is written in the way, but this is a vector. This is U1, U2, U3, U4, V1, V2, W1, P. So this is the system, right? Because when I solve, this is from 1 to millions of unknowns that you have. And then this is the matrix. But because you know you have a U, V, W, and P there, U1, V1, W1, P1, U2, V2, W2, P2, until UN, Vn, Wn, Pn, n being the number of control volumes that we have. Then you have a matrix. If it's coupled, you would like to have all your unknowns present in all equations. I always like to write very simple. This is an algebraic, of course, system of equation I'm going to write here. But when you have, let's say, I'm guessing something here which there's for sure no solution. 2x plus 1y minus 3 zeta equals 7. X plus y plus z equals 6. 3x minus 6y plus 7z equal to 0. Of course, this is, I have my equation here, you know, my matrix, x, y, and z. Here I'm talking about one variable. It's related to a vector there. This is 2, 1, minus 3. Here's my matrix equals 7, 6, 0. Of course, if I drop this one, there will be a 0 here, right? It shows up a 0 there. So it's nice to have all your system that you want to solve. it has all the variables, x, y, and z, x, y, and z, x, y, and z, to avoid zeros in your matrix. So it's nice to have all these equations, because this little matrix 4 by 4, it multiplies the first 4 values. Some value times u, another value times v, another value times w, another value times p. So this is the entries of this matrix are 4 by 4 matrices, because I'm trying to solve everything together simultaneously. What I want to have is all these numbers not zero, because if it's zero, especially in the diagonal, it will give you problems for solving my linear system, you know. And this is the picture how it appears, the simultaneous solutions for U, V, W, and P. I wrote there, segregate for the other variables. I'm already talking about that. So, but the simultaneous solution, this is the system. This is all the matrix. And of course, the entries in this matrix is something like that, you know. I will have if I have a 2D problem, this is just showing a part of the matrix. I will have another diagonal there, another diagonal there. So if you go far away from this matrix, you see the entries, which is the same as you have when you solve one single variable, you have one single value there. Now we are solving 4 variables together. I have a small matrix here involving the coefficient which multiplies u. And then it's nice to have in all your equation all the variables. And that's what we don't have in fluid mechanics equations. We don't have all the variables in all the equations. That's why trying to solve simultaneously requires some care in doing that solution. But this is the way the coupled system shows up.